Awesome. Thank you so much for the introduction, and thanks everyone for joining me. I know in my description I promised a lot of terrible puns, but this will be the only one I put up, so I apologize if that's a deal breaker for anybody. So what this talk is about at a high level, I want to talk about a journey that I embarked on at Target maybe around a year-ish ago in building out a text-based similarity engine to get some of our core data. And a lot of times we want to talk about the successes, the wins. I built this cutting-edge thing. This is how you should do it. But this is more a story of failure. I ran into a lot of issues along the way in exploring the linear algebra APIs in Spark. And so I just kind of want to share that journey with other people to help others who might be on the same journey now or in the future. So next I'll provide a brief basic linear algebra refresher. That'll be in the context of similarity engine since linear algebra is kind of a big field. And I want this talk to be self-contained so no one needs to come with any sort of previous expertise in any of this stuff. And then next we're going to talk about what does linear algebra look like in Spark? How do we scale up something that we could run on a single laptop to a big cluster? What does Spark offer? And then finally, I'm going to provide a lot of code examples in Scala. I primarily like to work in Scala with Spark, so I apologize to all the Python and R and Java developers. I imagine there are parallels for all these things, but unfortunately I don't have the playbook for every single language. So who am I? I'm a lead data engineer, data scientist at Target. I've been at Target for a few years now. I have a deep love of all things Target. I've loved them ever since they moved into my hometown when I was in high school, so it's been fun to join the mothership and do the sort of work I like after moving to the Midwest. Like Target, I also have a deep love of all things Spark. Prior to joining Target, I was able to work at a startup that kind of jumped on the Spark bandwagon early on. And it's been kind of love at first sight there, just kind of what it's enabled in terms of productivity and asking data across huge data sets has been really fun to work with. So I gave a talk last year at the Spark Summit that was pretty engineering focused. I'm giving another talk tomorrow that's also engineering focused on parallelizing with Spark in more unexpected ways. So let's get into our talk today. So first we'll dive right into the motivation. So here we've popped up a quick example of what a similarity engine might look like. So again, at Target, we have these core objects in our system that a lot of people care about. A lot of different business functions want to ask a question of, given this thing, what are the other things in our system that are similar? And so in terms of the small example on the left-hand side, you could think it's like these small sentences. You provide an input, and I want to know the top n sentences in our system with their corresponding scores that say relatively how good these things score against that input. And so with the system at Target, we wanted to first kind of produce raw data that people could look at and sanity check and see if it suited their purposes, and then eventually turn this into some sort of library or computation widget that could be pulled into different products. And then I started to join a group of data scientists who initially spun up the prototype. I came to them as a data engineer to help supporting the scaling of it. And so they started out working in scikit-learn and with PySpark. And they were doing this locally. And so they got something together that worked well on a small subset of data. The results look promising. People are excited about it. But as soon as we started to throw all of the data we had for this core object at Target into this system, it fell over miserably. And so that's where I came in to try and help the team and support them in scaling efforts. So let's talk about the nuts and bolts of what goes into a similarity engine. So to get everyone on the same page, the goals of the system that we wanted to build, we wanted to provide one input object, or a whole bunch of them, and the system needs to return, the n most similar objects where we could configure n to whatever we wanted. And then with the results that are returned back, we want pairwise scores that are kind of understandable so we can understand what's a better result versus another. We wanted to work off of a corpus of around 40,000 total objects. People refer to this as the documents or the features, so we're calling it the corpus. For this specific object at Target, this was around on the order of tens of gigabytes of data. So we're not talking about terabyte or petabyte scale with this specific data set we're working with. So you take that with a grain of salt with some of the things I present later on. If you are working at that much larger scale, some of this stuff probably won't work exactly as expected. Another requirement of this system is that we wanted it to support a vocabulary that had on the order of upwards of 15,000 tokens. So what I mean by tokens is we take all of the input features that are that raw text, we tokenize them, and we get the unique, distinct tokens in that set. So that's what our vocabulary is. And then finally, as the data engineer coming to help the team out, this was most important to me, was having this thing be performant. And so we set a benchmark. This was going to be a batch process running in the background, and we needed it to run on the order of minutes. So the team started out with k-nearest neighbors. And so there's a variety of algorithms you could use to apply k-nearest neighbors. Some are better than others. Some use approximations to handle the scale of data. But we went with 80-20 data science. We're going to do kind of the brute force method, see what we can get out of it, see if it provides reasonable results, and then iterate from there. So we chose the brute force approach with k-nearest neighbors. It's the most naive. It's considered an unsupervised learning method. The data, you represent it in vector and matrix format, so it's ripe for linear algebra math. And then as an end result of this algorithm, you're going to produce pairwise scores between all of the pairs of points in your data set. So for n samples, so in our case n objects, or n documents, or whatever your input features are, and then d dimensions, so in our case it'd be the d tokens of the vocabulary. The scale of this method is going to be on the order of dn squared. So the engineers out there, people who work in Scala, will look at that and groan and say, that's not going to work. It's going to blow up quickly. And so we figured for the upper bounds on the size of the data we were working with, that we could potentially overcome those scale issues just by throwing a ton of resources at it and farming it out to a Spark cluster. So when you pick your algorithm for k-nearest neighbors, you also need to pick how you're going to do the scoring. And so we chose cosine similarity. So this is a great metric that basically takes the angle of two vectors in a multi-dimensional space and provides a value between 0 and 1 to indicate how similar those vectors are. So I'm going to go through some examples of kind of end-to-end. How do we get our data in a format that we can start doing math on? So first step is we're going to collect your raw features. So our features are these 4 tiny sentences. And then the next step after this is we want to build a feature vocabulary. So like I said, that's basically looking over all of your raw input features, taking the unique set of tokens across all of them. And so you can see the vocabulary that shakes out of this input set is the, quick, brown, fox, slow, orange, cat, a, dog. And so for people who work in NLP, you already see some red flags there. I've included the and a. Those are typically removed as stop words since they're usually present across every single input and provide no meaningful signal. But I just kept them in there for demo purposes. And so the next step is you take that feature vocabulary and then you line it up to each of your input features and note where that term is present and where it's not. And it looks like binary vectors here. And typically you do what's called either count vectorization or something fancier if you want. And so if there were multiple repeats of these same tokens, like say you're processing a whole article of text, then you'd likely see numbers other than just 1. And so then you take all of your features, smush them all together into your big feature matrix. So now we're ready to start doing some math on this thing. So let's talk about cosine similarity. So this is how we want to get the pairwise metrics generated between each of the vectors. So like I said, this is a measure of similarity between vectors that is a measure of the angle between them. So as the angle approaches 0, this metric approaches 1 because they're really similar. If the vectors are orthogonal, there's really no overlap, and so the metric will approach 0. And then it ranges from -1 to 1, but we typically work in the positive space since we're dealing with positive feature vectors. And so this is a really great metric. It handles sparse data well, and it handles multi-dimensional spaces very well. And so the math for it shakes out that the dot product of A and B equals the magnitude of A times the magnitude of B times the cosine of the angle between those vectors. So if you reorganize the math around to get at that cosine, which is going to be your metric, it's the that turns into the dot product of those two vectors, a dot b divided by the magnitudes of a and b. And so that math is actually very straightforward to carry out. It's just the sum of the pairwise multiplications across all of the elements in those two vectors. And then the magnitudes are similar in the square root of the sum of each element squared. So if we just take a quick example so you can see what this looks like. We grab two features there, or raw features, the quick brown fox and the slow brown fox. We used that same vocabulary vector we found previously, vectorize those using the count vectorizer. And then taking the dot product of a and b, a lot of terms knock out because there's a ton of zeros, and so we see an overlap of 3. And then we take the magnitudes of both of those vectors. It's the square root of 4, and then combining that all together into a score is 0.75. So how do we take this from vector to a matrix? We want to operate on matrices wholesale because this is going to be our feature set that we're trying to learn the similarities for. So the first step is you got to normalize your matrix. So for each vector in the matrix, you're going to normalize it by the magnitude of that vector. So this will take care of the denominator of that cosine similarity score. All right, so the next step, when we actually want to get to the scores, we need to multiply that normalized matrix by its transpose. So matrix multiplication is going to grab, for each row compared to each column, you're going to line up the row and that column and then take the inner product, which is exactly the numerator of the cosine similarity calculation. And so that'll produce a new matrix, a square matrix, which is going to contain all of your scores. So you can see it produces a square symmetric matrix where the diagonal is all 1, so that indicates a feature is perfectly similar with itself. You kind of have redundant data, it's repeated there, so 50% of that data can be ignored. And then what this is indicating is you line up each of those input features against a row, and each of those input features against a column, and then you have where they meet is where is the similarity score of how similar those features are to one another. So for example, the quick brown fox, you grab that first row, and then you can see it's 0.75 similar to the slow brown fox, and then 0.25 similar to a slow brown dog. So now we understand kind of the nuts and bolts of pulling together kind of a rudimentary similarity engine. So the next step is we've got to move this thing to Spark. So how can we do the same thing but at scale? So instead of dealing with just 4 features and 9 vocabulary terms, we want to deal with upwards of 40,000 features and upwards of 15,000 vocabulary words. We want to be able to distribute this computation out, leverage the scale of a cluster, and then importantly, we want this to be performant and reliable. So the next step is to kind of dig into what is available in linear algebra in Spark. So this work was completed using Spark 2.2, around a year ago, and we're obviously a couple of versions ahead at this point. But the linear algebra package, space in the Spark ecosystem hasn't really changed since the version, so this is still really pretty relevant. So when starting out, I wanted to see if Spark had its own KNN library and MLlib, but it turns out it didn't, and so that's okay because we understand how to do this math at a low level with linear algebra, so the next step was to dig into the APIs that Spark provides for linear algebra. So let's start with kind of the foundation here. Spark provides a local vector, so it has int zero-based indices, double type values, supports sparse and dense. I grabbed a screenshot of the official documentation from Spark showing the different ways you could create the exact same vector that has 3 elements, 1, 0, 3. So you can see that you create a dense by specifying every single element out, and there's a couple ways to create sparse vectors. And so these are the vectors that are actually passed around when distributing the work out. They're stored on local machines, and it's a building block for Spark's local and distributed matrices. These are the distributed matrix APIs in Spark. And so the first 2 on the left-hand side are probably the most intuitive to me from the classes I had in linear algebra a while ago at this point. And so a row matrix and an index row matrix, these are row-oriented matrices, and they're backed under the hood by RDDs. So you have an RDD of vectors for the first case, and then RDD of index rows, where an index row just maps, or it just wraps an index and then a vector. And on the right-hand side, you see these sorts of APIs in a lot of the other libraries as well. So there's the coordinate matrix, where each entry is a tuple of the row index, the column index, and the value. So these are really well suited for very sparse data and where the dimensions are huge. And then the final matrix API is a block matrix. So this, again, is distributed matrix backed by an RDD of matrix blocks. And the block is basically an index of where that matrix starts, and it passes around small local matrices as a part of this big data set, or RDD. All right, so at this point, I'm going to transition over to talking about the evolution of building this system in Spark. I'll provide a whole bunch of code examples here. We'll talk through them together. Again, these slides will all be available after. I know we'll probably go through this a little quicker than it takes to digest everything, but it should be put online, I think, in a month or so. So we can assume, so at Target, we're building against a core set of objects. We can level set here and pretend we're going to build a similarity engine for articles. We can say we all work at like a content management company, and we have a system that has articles, authors, and comments. So the goal of our system is we want to input one article and then get back the n most similar articles to that input. And so we're really just going to follow the playbook from the linear algebra refresher on what a similarity engine takes. So the first step is we need to convert our data set of articles. We need to get those into tokens so we can generate a vocabulary. So we can leverage Spark's regex tokenizer to take care of that. And then you can specify how you actually want to split up your text. And so I'm splitting there on white space. But you can do fancier things like strip punctuation and lowercase. But I figured just keep it simple for demo purposes. And then really quick, I should note, there are the two packages in Spark for machine learning. There's ML and MLlib. ML is the newer one that's backed by data sets and supports pipelines, whereas MLlib is the older legacy one that supports, or it's backed by RDDs. And so I try and pull in the ML ones wherever possible, so that's what these examples are grounded in. But some of the linear algebra stuff was never moved over, so that's kind of in the MLlib space. So I just wanted to call that out. So after we've tokenized our input articles, then we need to go about turning the tokenized, the bag of words representations of our articles into vectors that are laid against the whole vocabulary for all of those articles in our corpus. And so we can use Spark's count vectorizer. Like I said, there are fancier ways to do this. One way is using a TF-IDF vectorizer, which is like another NLP tool for kind of getting at novelty of terms. But the count vectorizer is a good kind of baseline to get started and just see how it performs, and then try the fancier things later. And so you actually have to create a model for the count vectorizer and fit it against your input, because you need to have the view of the whole vocabulary. And then you can take that model and transform your input data set so you do get those vocabulary vectors filled in on a per input feature basis. So this works great. I've used this in other applications when building Spark projects, and so there's really no problems here. So the next step, when we actually want to start doing the multiplication and get at that measure of similarity through cosine similarity, the first step is to normalize our matrix. And so we can use Spark's normalizer feature generation tool, and then you just set the p-value. So p here is 2 because the magnitude of a vector, we use the L2 norm, which is also called the Euclidean distance. So it's pretty straightforward to configure all this stuff. And again, this normalizer works great, no problems there. It's very straightforward to use. Okay, so this is where things started to go very wrong for me. This is where I wanted to take my big distributed matrices and then multiply them by each other, or multiply by itself out transposed. So this is how I got started. I'm trying to fill out this generate pairwise scores method that's going to take in those raw features where they're represented as that vocabulary vector on a per input feature basis. So I decided to start out with index row matrix because that seemed most intuitive to me, why not? And so to create that, you have to pass in an RDD of indexed rows. So those first couple lines of code there, let's see, 122 through like 123, is where I'm just creating that matrix from those input features. And so then I figured, okay, I have my matrix. I can just go feature matrix times feature matrix dot transpose, and this should work, right? And so it turns out it fails miserably because it doesn't even compile. And so what did I learn from this? I learned that transpose is only available on the block matrix and coordinate matrix APIs. I learned that multiply, when you want to do it on two distributed matrices, is only available on the block matrix API. You are able to multiply the row matrix and the index row matrix by local matrices, but I really wanted to keep things at the distributed level. And so kind of given all these constraints, I decided that the block matrix was the way to proceed. So here's my next attempt. So the code above is all really the same in terms of creating that feature matrix to work with. So a lot of these APIs have convenience methods of converting back and forth between the different distributed matrix types. It's kind of an expensive operation, so I figured if I got this working, then I'd rework that code just to start out in the right matrix type as a block matrix. So here I go feature matrix, convert it to a block matrix, then multiply by that same matrix transpose, and then convert it back. So this code compiles, which was exciting. And then I shipped it out to a Spark cluster, fired it up as a job, and then it fell over pretty fast with out-of-memory errors. So if you look kind of deeply at the stack trace here, we see that within the block matrix API, it's converting sparse matrices to dense. And there's no way around this. It's just in the bowels of the Spark code, and there's no good way to configure it. And so it turns out, for this case of generating these feature vectors against vocabularies, they're by definition going to be very, very sparse. And so this was, likely blowing up data, hugely in a way that's kind of unexpected, at least how I thought, these APIs would work with their multiply. So you can configure the number of rows and columns contained in a matrix block, to make the trade-off between having smaller matrices that you're passing around and doing more computations to kind of alleviate some of that memory pressure. But I kind of just wanted to avoid the fact that this was converting too dense in the first place, because you can do matrix multiplication on sparse matrices, and you can transpose sparse matrices. And so I did actually try this out as an experiment, and the job started running, and it ran and ran and ran, and then an hour later it fell over with out-of-memory errors. So I still kind of had the same result, even when I tried to tune the block size way down. So back to the drawing board. So it would be ideal to stay in the sparse representation of these vectors, given how sparse they were. So the first idea I had was to switch to the coordinate matrix API, because by definition, it's well designed for this kind of data. We have, big dimensions and very sparse data. But this also seemed like it would generate, so I wanted to switch to this matrix format and then manage the multiplication and transpose myself by just kind of keeping track of all the indices. But if you remember from the earlier slides, this operation of multiplication is going to be an n-squared operation. And so it's kind of like doing a self-join in Spark. So if anyone's ever taken a big data set and then tried to join it to itself on some non-unique key, you most likely saw your cluster screech to a halt and then job progress stall, because it's doing this many-to-many join, creating a huge shuffle stage. And so I was going to hope to avoid this. There are some optimizations you can make to try and speed that sort of thing up. But I figured I would table idea one, keep it in my back pocket if something, nothing else shook out. So then I moved on to idea number two, which was to go back to the index row matrix and then try to leverage the fact that you could multiply by local matrices. And so this seemed kind of promising because we could take out our original matrix and then broadcast small chunks of it out to the executors to take care of the local multiplication. But when I dug through the source code of how this multiply worked, I also noticed that there was the too dense conversion as well. So it seemed like I'd probably run into the same issues with this method. So the last idea I had was to wrap sparse vectors in a data set, or RDD, and then kind of manage the linear algebra myself through the executors and the tasks. And then again, try and broadcast out smaller chunks of these vectors for that multiplication by the transpose. Reassemble these vectors into matrices locally, and then take care of the math at a low level. So this approach ended up working in the end. There were still more bumps along the road, but this ended up giving us a solution that was performant and ran on the order of minutes like we were hoping for. But I'll continue to talk through some of the bumps. So just to get going with this idea, I decided I'd create my own little case class, kind of like the indexed row, and I would wrap an ID, because I wanted to keep track of the IDs of the objects I was trying to get similarity for, and then wrap a vector. And I tried to wrap a strongly typed sparse vector. And so the generate pairwise scores function looks really similar to what I was doing before. So I'm going to generate, a feature vectors data set where I map all of my raw, vector inputs into this my sparse vector object. And so before I decided to go through all the analysis, I just, wanted to take a look at my data and make sure it looked okay. So I cached those feature vectors, took 10 for each print line. And I got a super cryptic error, dumped a whole bunch of generated code from Spark. And so this is kind of a tangent. It has nothing to do with linear algebra, but I figured I'd call it out because I ran into it and it was weird. But Spark can't serialize or deserialize sparse or dense vectors. You can only serialize vectors because of the vector UDT, the user-defined type. So the user-defined type allows classes to specify their own way of serializing and deserializing to work better with Spark SQL. And this API was locked down and made private, I think, post Spark 2.0. But this does exist for this vector space. And so I ran into that. And so I had to switch from wrapping a sparse vector to a vector and then do casting, which was kind of gross, but that was just the way to work around it. Yeah, so this, I'll probably skip through this because I just talked about it. But here's a code snippet I grabbed from the actual Spark source code. There's a reference there that just dumps what the vector UDT looks like. And so you can see it manages the serialization and then also the deserialization that you don't see. And it's basically managing those finer types itself. So it knows how to serialize those and then grab them back out, but still kind of operate at a high vector level. So we finally got something that was working. To put together kind of an end-to-end thing for the purposes of this demo ended up being a little bit too much code. And so what I put there was just a couple of examples of how to interface with Breeze to convert Spark vectors back and forth between Breeze. So just to reiterate what worked for me was wrapping these vectors in a data set and then managing the partitioning of how many vectors I wanted to work on at once. And then also broadcasting that same data set of vectors in smaller chunks. So the idea was to do smaller chunks. I was actually able to get away with shipping out the whole thing because it was so sparse, and then keeping track of the indices when I got to the executor level in tasks. And so I was able to grab the partition of vectors, grab the broadcast of vectors, and then take those and use this list of vectors to matrix function to take those vectors, turn them into a Breeze sparse matrix representation. And then to actually get the scores, I leveraged this compute pairwise scores function at the bottom, which is going to operate on Breeze sparse matrices. And then it does exactly what I would have expected to do in those early slides of how I thought the APIs should work. So other bumps along the way, I learned that matrix multiplication, as expected, is very heavy, causes spikes in memory. So you can tune your cluster to handle all of the data that you're partitioning out in terms of all those vectors, and you can tune the memory to handle all the broadcasts that you're sending out as well. But then you also have to account for the actual raw calculations that are happening, because it's keeping that running tally, the running sum of all the pairwise multiplications. when it's going through each row and column to do the scores. So that was something I ran into and had to tune against. So I figured I'd call that out. So that's basically it. These are all my lessons learned. So some of the core matrix operations, transpose and multiply, are not available in all of the distributed matrix APIs. It's going to convert, if you're going to use the block matrix API to do the multiply, it's going to actually convert things too dense on you, which I didn't expect. Under the hood, Spark uses Breeze to do a lot of the low-level linear algebra. Breeze is independent of Spark. It's a numerical processing library in Scala. It supports, linear algebra, but also optimization and other facets of math. And so if you start to dig through some of the source code in Spark, if you look at like an eigenvalue decomposition or singular value decomposition, you'll notice, the similar pattern. You take the Spark vectors and then convert them to Breeze and then do the low-level math. And then there are convenience methods in Spark to convert back and forth, but those are marked as private. So you kind of have to reinvent the wheel if you want to execute a similar pattern. This is the tangential thing, but sparse and dense vectors can't be serialized if you want to ship those around in data sets or RDDs. And so you have to represent those as a higher level vector due to the vector UDT implementation. And then I'll just call it that matrix and vector multiplication is heavy in Breeze, and so you kind of have to account for that and how you're tuning your memory settings. So with that, that's basically it. I didn't plan to come today to say, this is the state of the art, this is a shiny thing that worked really well, this is how you should be doing this. We did a really crude method trying to do 80-20 data science. I ran into a lot of problems along the way. I kind of noticed, some of the Spark APIs in this space don't get a lot of love. And, people might ask, why didn't you, try a TensorFlow? It seems like the community's shifted in that direction. Really, I just wanted to see what was possible with Spark with the APIs provided. So it was, eye-opening, a good learning experience, probably a personal call to action to, get involved if I expect an API to work a certain way, understand the conversations that, the developers are having and contribute possibly. So I won't, I absolutely love Spark for what it is, and I won't knock it, for a misconception I had about how an API should work. So yeah, so overall, it was a fun learning experience. So here's my quick Target plug. Consider working for Target. We're hiring in data science and data engineering. We have offices all over, and we're headquartered in Minneapolis. It's a really fun place to work just because of all the data. The retail world spans supply chain all the way to execution in stores. So there's just a lot of fun facets of the retail world to get into. So you can check out our job site or contact me if you're interested. And so finally, acknowledgements. Thank you, Spark Summit, for having me. Thanks, Target, for sending me. Thank you to the wonderful people I work with at Target. I want to give a quick plug. My colleagues, Doug and Patrick, are giving a talk tomorrow on a data validation framework they built for Target that they've open sourced. And so I encourage everyone to check that out. And then thank you to all of you guys, Vibrant, Spark, and Scala communities. Definitely learned a lot from all of you. So thank you. And then with that, questions.
Yeah, so if people have questions for Anna, there's a mic there, and I'm also happy to run to people with a mic.
Hi. Not really.
Hey, so I just went through this entire journey about a month ago. So did you try the column similarities method within, I think it's the row matrix class, which actually does a cosine similarity? Look, I had expectations about an API too. What's really weird about it is computing the similarities between columns, which doesn't make sense being that almost everybody has their objects in rows in Spark. But did you try it?
I vaguely remember that. I think it was a little while ago at this point. Like, what API? Is that on the data frame API that's
no,
exposed?
it's in the linear algebra package.
Oh, it is?
and I know that the guys at Twitter contributed to it. They've actually got a statistical approximation within it that speeds it up. But again, you basically have to go through all that work to convert it to row matrix, block matrix, transpose it, so you can do the column similarity.
Yeah, I think I maybe didn't put the pieces together to get the transpose working where I could have tried it. I may have tried it first and said, well, this won't work because I have everything in row format. But yeah, that's a good point. Like I vaguely remember that, but never got it working successfully. Yeah, thanks for the question.
Oh, that one's working
How do you handle deploying that and making that available in a production kind of setting?
Yeah, so I'll typically build these jobs with, a Scala package, and also I'll use SBT, package it up as a fat jar, and then we ship it over to edge nodes, and like for testing purposes, kick that off with a Spark submit. And so we are able, I've leveraged, ideas that have been presented at summits in the past for, unit test suites where you use a local in-memory thing, hook it up to a, Derby, Hive, Metastore, create subsets of data to actually do unit tests. So I don't know if that answers your question, but we have the CI/CD capabilities around it to leverage, the SBT build setup, and then we also kind of incorporate unit tests as well. Is there a specific thing you're after? Oh, that's a good point. Yeah, so this is kind of still in prototype mode, and so we would just kind of expose the code to people so that they could build a jar, ship it out, and try it themselves. We, initially exposed the data so someone could go play in the data lake with what was exposed, but wanted to make it configurable, with different algorithms or feature representations. But yeah, we didn't get to that point.
Yeah.
So I remember back in graduate school, and I have a PhD in mechanical engineering and computational science. We used to use MPI for parallelizing stuff. So I remember there are sparse implementations for linear algebra and C++. They are already available using MPI. So I'm not sure if a lot of data science people know about the MPI and OpenMP and all of this stuff. So have you tried any of this?
Yeah, no, that's great to hear about. That's something I'm not as familiar with. So yeah, okay. I wonder kind of how that would interact and play if you wanted to try and do it in a Spark ecosystem.
Okay.
Yeah.
Thank you.
Thanks.
Okay. Any last questions before I have to hit the time mark? Okay. If not, then let's give another round of applause for Anna. Thank you.
Thanks.